Okay, let me start this our PRP session at this APAN the his meeting, and our working group is the same. It's 2018, and initiate on the 45th in Singapore, and our objective and the target is the screen, and when we meet the APRP working group days, I mentioned about this. I want to skip this, and at this APAN is the present it's 16 presenters and 8 countries comes 8 countries. So I want to briefly introduce the first session. I wanted to name the first keynote speech and the country of the second presenter is Yves, and the keynote speech, and he can tell us about kind of global research platform related work, and I think it include is our activities where we set the proper directions. And the third is, and me is, I wanted to update Asia Connect project. So, and the fourth, Nura Asilah Wati Abdul Hamid, she came from the PM from Malaysia. She can tell introduction of Malaysia HPC and the future work. She is one of the core PIs Asia Connect project. So she will show their status and their the fifth and the sixth and the Kihyeon Kim he from Korea and KISTI he the country update of Korea the name is RD2 project Korea the Kihyeon is short and provided is such like these the research platform to Korea the institute for the government funded. So and the sixth and seventh and from Asif Raza, the presentation is 2 times, and the one is network state of our Asia Connect project, and the second thing is the Pakistan country update. And the next thing is section 2, and the first present is Andrew Howard, and he is the chair of section 2. The from 1 to 10, and the closing is me, and we have 10 presentations left, and meeting I think is very a variety the presentation topics from Asia Asia is the corner is Turkey. Turkey is not is the Asif Khan. So students, 2 students, and the presentation their work. It's related as a bioscience. Asif Khan from also the co-PI in Asia Connect project. So this is briefly our the APRP session. So under the finishing in my introduction of the APRP session, and this and its part, and he will talk about keynote speech for 20 minutes for the global research platform and so on. Okay, it's part. Are you ready? And go ahead.
Thank you, Jeonghoon.
Yeah.
Let me try to share my slides.
Okay.
Okay. So thank you very much. I will not take too much of your time. I think most of you are quite familiar already with our research platform exercise. And before everything, I want to congratulate Jeonghoon and the team for the award they just got in Jeju. So this is great news, and this is really proof that what you are doing is really of a value. And again, it's a noble cause to want to have everyone trained and educated wherever you are in Asia or in the world. So this is great. So research platforms. So I put the XRP because there are quite a number of research platforms coming around. And if we look around here, let me see. First of all, as we know, our research platforms, they run on, in fact, let me put that. So I think it's better like that. Mm-hmm. Okay, so our global and research and education network, which carries our research platform, has grown a lot, and the additions over the last year have been essentially the links from Singapore to Europe. We have 2 times 100 gig, in addition to the link we have, which is not shown here, I notice, and which runs from Singapore to London. Trans-Pacific, the capacity has been increasing also, and it continues. In fact, at the APONET meeting yesterday, we heard that Japan will have an additional 100 gig to the US, and then an additional 100 gig also to Europe. So things continue to grow, and then also next year between America and Europe, there will be the first 400 gig links. In fact, one will be Montreal, so the Canary network in cooperation with Internet 2 going to Europe, and the other 2 times 400 gig will be by ESNet. And on the Pacific side, the first trial took place on the new Next cable at 400 gig. So we can expect that in the next couple of years, we will also see a lot of capacity coming online on the Pacific, and then of course within Asia also. Now, why R&E networks and platforms? Again, I'm preaching to the convinced. Big science is still dominating, and in fact, when you think big science, even in Europe, I was surprised that the Jeonghoon network, for example, 50% of the traffic of Jeonghoon is CERN, so that's a Large Hadron Collider. And we all know that the 3rd run has started on July 1st, is generating quite a load of traffic, and of course has also to be connected and carried in a secure way. So basically they have their own little research platform and have had it for years. If you look at another big project we're all really curious to see taking off is a SK80 square kilometer array in South Africa and Australia that will also generate loads and loads of traffic and will really fill our networks. And of course, you also need a kind of a science DMZ catering to the astronomers. The same for ITER, and which is the fusion reactor in France, etc., etc. So again, the instruments are so expensive. The only way to use them is to collaborate and to share them. And if we go to material sciences, to genomics, to meteorology, we have to share also. We've seen COVID, which is now often cited as an example, as a sharing, and obviously humanity has quite a number of grand challenges. So again, why the research platforms is to really allow all our scientists in a distributed environment. The key is distributed, and have equal access to computing power, to storage. Storage is more and more important, and also to instruments. And again, the award now given to Syed Jeonghoon and the team is again to go and share the access to resources, computing resources in this case, located in Korea and in Australia, by Malaysia and by Pakistan. And again, we're all talking about HPC as a service, HPC AAS. We're also talking about the hyperscalers, as we all know, AWS, Microsoft, Google. They also try to convince the R&E people, amongst others, to join them. Again, it is better that we have these services provided by the scientists for the scientists. And again, we can also use the commercial networks, but we have to be careful of the cost element and also, of course, of the national priorities. Aprp was born in 2017 in Dalian. Jeonghoon and Andrew Howard were chosen as a chair and the co-chair. There were a number of meetings, APAN, because the APAN rules is that you have to have 2 meetings, then the third one, you become a working group. There was, of course, the COVID in the meantime, and now we are meeting again and virtually, and we all hope that the next APAN 55, which I think will be in Nepal early March next year, will really be an occasion for all of us to meet each other. Another element which is quite important and has grown over the years is the Data Mover Challenge. So the object of the Data Mover Challenge is to award the best team who has the best way and the most effective way to transmit data between a number of places. And Andrew Howard is the chair and the lead of the judging committee. Asia Connect has been a key enabler of Aprp, as we all know. There have been now 2 projects. One is the first project where Singaren was a PI with Lawrence Wong, and that was completed in December last year. And now we have the second project, which is headed by Jeonghoon and Andrew, and with the 2 Asifs participating. And again, that's in progress, and we will hear much more about these projects at this meeting. That we know, again, high bandwidth, distributed, the famous distributed, and in a science DMZ context. And of course, the access to CPU and GPU is quite important. The Kubernetes has becoming the de facto standard everywhere in the world, so that's important. The project last year. Now, the highlights of SCA Aprp, as we have said, you can watch a number of these presentations, and again, the highlights was the AMDEX. AMDEX was presented by Kees de Laat. That was quite an important contribution, and what they basically try to do is to have a data exchange. So again, all on the theme of storage. And Koust gave a genomics presentation. We'll hear from Alex Morrow later in this presentation. So this is very important. In fact, we also have now SCA 23 coming up, and we hope to have again an Aprp session. There will be no DMC because DMC is every 2 years, but the new DMC will be announced. And again, we also had a mini GRP, the Global Research Platform, and that was headed by Professor Joe Mambretti from the US, from Chicago. Some highlights of the the mini GRP, again, very important. This is a big science, and in Singapore we like genomics because in Singapore we don't have a Large Hadron Collider and we don't have an SKA. And of course, Korea always provided very interesting presentations because they are also always #1 in implementation. I would draw your attention on the next GRP, which will take place in October 10th and 11th in Salt Lake City, Utah, and I hope a number of you will be able to attend this third GRP. What I illustrated here is one of the NRE, the network research experiments, which will be presented at the SC, the Supercomputing 22 in November in Dallas. And this is Harvey Newman's project where, in fact, quite a number of us are involved. And in total, I think they will have 4 terabit of capacity running to Dallas this time. So this is really something. And I also would like to point out that there will be a connection from Singapore, Singaporean, to Coast, to Europe, to America, and also one on the other side of the ocean. So it will really be a ring. Now, the US model we have been following that has gone from a PRP, so the Pacific Research Platform, to NRP. In fact, we just had a call with Frank Wiltwine, who has been nominated the PI, Principal Investigator for the new NSF award for the creation of the National Research Platform, which is phase 3. So basically we had PRP, which was headed by by Larry Smar, of course, and then we had the second phase, which was towards the National Research Platform, so TNRP, and the third phase, which we now have, is the famous National Research Platform. And again, we all learn from there. Now, if we look at the next phase, SDSC, so the San Diego Supercomputing Center, where Frank Wiltwine has just been nominated the boss of the HPC Center. He will play a major role. And Larry Smar, again, he explains what NRP is all about. Again, we don't have to repeat it here. I think the last sentence is quite relevant. If you're going to see this type of cyber infrastructure become a permanent part of the research landscape, completely distributed, high performance. Again, the permanent part is very important. We had a number of discussions on that subject also, the need to have the platform become a permanent setup instead of just something for a demonstration. This is, again, what it will look like in the US. A number of lessons have been learned, which we have to mind. One is to sustain. Again, we have to plan something together to have this effort continues once the project funding by Asia Connect starts. So we have to avoid that by the end of this year, the projects halt because of lack of money, and that we all go home again and wait for the next project to come about. So basically, this brings me to the way forward vision for APRP. We need distributed computing and storage, as well as cloud services. Again, this is a cloud service environment you are now experimenting, and we need that to be permanent. after January, Pakistan has to continue to be able to access computing resources, to access storage resources and instruments. And I think we all have an obligation to facilitate that and make that possible. Again, suggested next steps are quite straightforward. I think we should try to expand the APRP topology in Asia by trying to combine the two Asia Connect funded projects. We should also make ourselves more visible, present, for example, at the GRP workshop, and plan joint demos eventually in December. Then I think we should try to standardize and document the APRP implementation. One example is DTN configurations. There are quite a number of DTN variations around. We should try to have a common DTN recommendation. Then we have to actively deploy national science DMZs. And there again, I would congratulate Korea and KISTI to have moved quite fast. In Singapore, we are preparing a mini research platform. Again, Singapore is not that big. We have a half dozen major stakeholders. So basically, they together will create a science DMZ. Then also we should evaluate what the US is doing. They have quite a number of interesting projects, like they opened the Open Grid. They have the Noted, which is work with the Large Hadron Collider, with the CERN people. There's FAB, which is very high speed, etc., etc. So in other words, I think we still have to be creative and let go of certainties. So that will close my little intervention. If there are questions or comments, they're of course most welcome.
Yes, thank you for the presentation. Anybody the question about that? May I have a question about this contents? What do you think about this? What is the major battle to deploy globally? Such like the research platform, a big data superhighway, as a GRP, the viewpoint of GRP.
Yeah.
The current.
Well, yeah. I think, well, first of all, we have spent quite a number of years to deploy the NRENs, the National Research and Education Networks, connected to each other, which has been a long and difficult exercise. In fact, the difficulty essentially came from the pricing. This is one aspect. The drivers for these high speeds have been essentially. Do you also hear an echo, by the way? No. Okay, yeah. Okay, echo is gone. So the second layer, so as I said, the first motivation was big science and continues to big science for these big data networks. Now on the second layer, to have collaboration in certain domains is easier than others. I think, for example, astronomy people, it's easy to have them work together. Physics people, it's relatively easy. Where you will have more debate is in biosciences and genomics, because there you have the privacy issues always pointing their nose, and with justification. And obviously there we need to also pay attention to the storage aspect. And obviously another aspect also we are looking at the hyperscalers, which are at the same time our suppliers, our partners, and our competitors. So because talking to some universities and some research people, they say, why not go to AWS or to Microsoft? And again, this can be very reasonable if the volumes remain small. So in other words, one has to be careful, and one still has, in my opinion, if we have the choice and the alternative, to give the choice to our networks, especially if we collaborate. Because if we don't collaborate or if we don't share anything, well, then, in fact, there would not be the need to have our networks and our research platform. Again, the key is distributed. The key is DMZ, so to have an unimpeached access. And another component is security, and there the identity federation, etc., is extremely important. So in other words, I think Asif should be able to sit in his lab, access instruments, access supercomputing power, and access storage and information when he needs it, and if he needs it, and at decent speeds. This would be my answer.
Thank you. Thank you for your answer and your presentation again. Does anybody cast for the IFAP? Okay, I know one thing more. Yeah, in advanced countries like US and European, they have a high bandwidth the backbone, and the major point is they very easy to access the super facility. In case of Asia region, and we still have the last one my problem, even though we provide this NN. So what is your comment or your opinion for how to upgrade this and areas to as a strategy?
Yeah. So you're referring to the access speed from a certain research networks. And of course, research networks, the access speed or the speed between networks. Now 100 gig, if you look at the 100 gig networks, the first 100 gig connections were 10 years ago, in fact 2013, between the US and Europe. Then the first one was Singapore to supercomputing, 14 in fact. Now these were still expensive. Now 10 years later, the prices have come down, and that has allowed us to have these 100 gigs. Now, the only reason we have 100 gigs is that we have introduced cost sharing. And so cost sharing between different national research and education networks, and also buying IRUs in the feasibility of right of use for 10 or 15 years from the suppliers, and buying unprotected connectivity, which then is more dangerous, of course, because you don't have backup. That was then solved by putting networks together, like we did with APONET, like we did with AER, like we did with APR, where we basically emulate what the carriers have been doing for a long, long time. So this is one thing. Now the other aspect, and that's where it becomes more difficult, is that not all countries are as liberal in the provision of their capacity. And prices in Pakistan, for example, are much, much higher than they would be in Korea or in Singapore. So I think we collectively have work to do still to convince a number of administrations, quite a number of administrations actually, to liberalize their telecom. It's a difficult task, or at least to have a special arrangement with their national research and education community. So in other words, the Minister of Telecom should speak with the Minister of Education. This is very important.
Okay, thank you. Thank you again for your presentation and the answering. So, okay, the next presenter and me, I'm going to start in the presentation. Would you please stop the share screen?
Yeah.
공유됐나 좀 봐주세요. 하나군요. 이렇게 하면 뭐가 뜨죠?
이렇게 하면 집에 안 넘어가면 놀라시는
거예요. Okay. Let me start. Hello everyone. I am Jeonghoon, working KISTI in Korea for especially the working for Kihyeon, which is via research and education open network. And also I am in charge of Aprp working group in APAN, which is a prospective research platform working group since 2018. Today I will talking about this data of Asi Connect, which name is building a high bandwidth with distributed HPC. It had passed the 5 months from 1st April of this year. So I want to introduce briefly this project. As I mentioned, the project name building a high bandwidth with distributed HPC. It belongs to package 4 of Asi Connect project by TEIN. And the participant countries are the 4, which is the Korea, Malaysia, and Pakistan. And duration is from this 1 year, from the 1st April of 2022. And the budget is on this 150 euros for 1 year. And the applicant is me, and we have 4 co-applicants. Those are Andrew Howard from Australia, Asif from Peradama University in Malaysia, and Nuru Asilah Abdul Hamid from UPM from Malaysia, and Sida Shah from Sukkur IBA University in Pakistan. And this slide is of this project. I mentioned several times, but newcomers at this time. The data explosion in science and technology, there was the demand for high capacity networks for accelerators, storages, and collaboration simultaneously. It brings many restrictions on the generation, transmission, and the utilization of research. In recent year, the ESNet, UCSD, and the KITI2 in the US have utilized the big data superhighway to send and share scientific big data with the leading research institute, university, the institutions at ultra high speed. In the case of US, it was carried out as the national project advised by NSCC, Connecting Science and Technology Research Institute in the west part of the US to Science DMG, and enabling high-speed transmission of big data, called PRP. In addition, this big data networks entered infrastructure systems expanding and developing into the global environment. We can call this is GRP. The purpose of this project is the method to enable the public high-performance computing resources to be delivered to the developed countries in Asia through TEIN network. We propose a platform that transmits not only the data over the network, so computing resources. In this proposal, we aim to establish a science-based research platform and with the distributed HPC environment. And it will be shared in Korea, Australia, Malaysia, Pakistan. That is, we build high-performance computing servers that add the computing resources by CPU, GPU, and memory through a special designed high bandwidth network over TEIN. and it will be run for bioinformatics-based research in Malaysia and AI research in Pakistan. For example, Figure 1 that shows the distributed computing resources integrated through PRP infrastructure and the scientific result about the analysis using the distributed computing method. The Figure 2 shows the urban flooding research using the distributed computing resource and the science data of STM analysis method for climate analysis. The infrastructure links this to the platforms at many the research institute, the national research that is correct. And so this is a whole concept of this, the building a high bandwidth NN for among participant countries, and also establish big data superhighway, and then deploy distributed research platform for third-party application, the research which need the computing power or related big data. The role of each participant are the South Korea and also providing infrastructure technology for building and operation, and the Pakistan and Malaysia, the providing the application expertise. To implement this act, it is divided into 3 activities, and each will achieve the detailed goals. Activity 1 is building a big data highway based on TEIN. Activity 2, the building distributed HPC platform. Activity 3, the presenting pilot use cases. And from now, I can tell this the update, what we did the last 5 months to building a big data superhighway based on the 4 participants countries connected 105, but not yet complete. The Malaysia already connected with the KR and the AU testing now. Australia is testing now. The left picture is a retopology and in Asia areas, and right picture from Malaysia by Pana, which can monitoring throughput, the packet losses out, and so on among us. Asif Raza will have time to more detailed explore this from 6 of this session. And the second activity, the distributed HPC platform. The first of all, the participant, the status of infrastructure is left the picture. We can make the configure capacity of participant following the left picture is almost final. The Korea provided the node which consists of 2 GPU node and 1 CPU node, and Pakistan, Malaysia will provide 1 or 2 GPU node. About platform, it's almost set up complete. There are several functions completed, which are the Kubeflow module, the storage module, the monitoring the Kubernetes cluster module, and some of the functions are in which are the image manager and the code review module and the web interface, the login module so far. And the next slide is this is activity 3, which is presenting the pilot application use cases. We are the two types of application. We have 2 types of application from Malaysia. Pakistan is in charge of AI science action, and Malaysia is in charge of bioscience application. We are learning testing on this platform at this time with the CPU and GPU. The Asif Raza will explain more detail about that later, and also the bioscience will be explain the detail in session 2 by Asif Khan. When finished the setting up the platform and the data superhighway, we can show demonstrations sooner or later. This slide is from new news. I'm very glad to announce the happy news from the Asif Raza in this morning. They got the best paper award from 2020 International Conference on Platform Technology and Services yesterday. And this paper comes from the Bird project. The title is HPC for Asia, a distributed research platform for educationists and researchers of our country. The authors and the course and Asif Raza and Kihyeon Kim, Andrew Howard, Asif Khan, and Noor Silawati. All of the co-PIs are the core of this project. I'm very glad to his pleasure. And the last slide is my presentation. Actually, the remaining issues. Actually, I wanted to focus the issues in this project for the conclusion. So it comes from the three activities. The first is the big data superhighway. We have the last one my problem, the configuration each state of path. The other thing is the security policy problem. We want to make a trust zone and among participants. And the thing is a distributed platform. The difficulty is due to delaying the purchase of equipment. And the delivery and the set of issues we have limit issues. And the third activity is pilot uses. The building familiar the user experience need, and we need to install software required for applications. And finally, we have the test learning. Is the proper or how the benefit for the application areas. So far I trying to talk about building the high bandwidth distributed HPC project. Thank you for your attention and listening. Is there anybody question about that? Okay. There's no question. We have a little bit delayed, but don't worry. And we have to is the more 10 minutes. Next presenter is the Abdul Nuru Asilah Abdul Hamid from PM in Malaysia. Are you ready, Asilah?
Yeah, thank you, Jeonghoon. So I guess I would like to share my screen right now. Is it okay? Okay. So can you see my screen?
Okay. Okay, go ahead.
Yeah, I'm going. Yeah. Is everything clear? And is my voice also clear? Yeah. Okay. Good morning, everyone. Thank you, Dr. Jeonghoon, for the introduction. And my name is Nur Asilah. I am from Universiti Putra, Malaysia. And today I'm going to talk on Malaysia's HPC and future works, which suggested by Dr. Moon on the title. Okay, so this is my content. So I'm going to discuss or list out a little bit on the HPC available in universities and institutions, because I believe if I list down for the industry, maybe my knowledge is far beyond that on the industry HPC. And then I'm going to focus more on the HPC in UPM. I believe probably UPM can be representative of HPC situation from universities in Malaysia. And some survey, I would like to show some survey that we did for HPC in UPM, and field of study that demands HPC, and some effort or options to have HPC in UPM. Okay, so the latest university in Malaysia that purchased HPC, and I can say that probably this is kind of like a complete HPC that they have. I mean, the one that I categorize after this is the one that kind of like have a complete HPC, which considered as a head node, process node, and everything. So University of Malaysia of Nottingham, Malaysia, they just purchased NVIDIA DGX A100 recently for AI research and also for teaching. So this is the recent one. So the next university that have quite good and stable HPC is Monash University of Malaysia. So they Also have like 8 core, as you can see, 12 compute nodes with a total of 192 processor cores. So they have quite stable research in bioinformatics from as far as I know, quite active in bioinformatics research. Okay. So the third one is from University of Malaya. University of Malaya is the top university in Malaysia, and the one that are responsible in HPC maintenance is from the Data Intensive Computing Center. I believe this center already established quite a long time ago. I believe at least 8 years ago. So we can see that what they have, they also have quite latest, not really latest, but quite latest for the GPU V100. Okay, and they have done many research based on this HPC. So, okay, so this is actually the only 3 university in Malaysia that I believe they have units or section that manage HPC quite well, based on my knowledge and based from my research from the net. Okay, so right now, this is actually the one that we have in UPM, University Putra Malaysia. And so this is actually the one that I can see a complete HPC, which we established in 2012. And during this time, this HPC is actually dedicated for the grid computing to join the academic grade. So it has 8 nodes, but unfortunately, I believe it's almost 10 years and it's already outdated. And we are actually in the middle of getting the new one. So since the COVID-19, it's not easy to get the budget for the new HPC. So the other one that the rest of the HPC that we have in UPM, so that's why I focus in UPM. So beside those HPC that are already outdated, so the practice that I believe have been done in many faculty and even in my faculty and institute, that we just purchase like high performance desktop, just enough for our research. For example, like this one, we purchased one Quanta Grid with one Intel Xeon and one Volta V100. So, during this time, the objective is to give some exposure for our students and also manage to perform some decent data science for bioinformatic research, engineering, so and some other research. And we also, there are quite numbers of high performance desktop and also servers with the GPU, but most of these purchased before the COVID-19 in 2017, 18, and 15. So most of it is already outdated. And we are currently in the middle of a process to get the new one. And so I don't think we make it in this year because the budget is very, very tight. So yes, that's all for in the whatever HPC that we have in UPM. Okay, so this is our Quanta Grid. So I can say that this is very useful to us right now for teaching purposes, give some exposures on the GPU programming and also for data, big data, data analytic, and there are many users. At least they manage to run larger size of data that they can run on their laptop or desktop. Okay, I would like to present. So my next content is on the survey of HPC that we have done early this year. So the purpose, okay, so the purpose of this survey is actually to support our proposal to get HPC, to replace the HPC. So this survey is still continuing because we try to get more responses. So right now we have like around 100 responses. So we can see this is actually the responses per faculty and institute. And okay, so the next is showing the responses based on role, lecturer. So we have many responses from lecturers, research officer, and also PhD students. And the next is actually, okay, so I accidentally skipped. So this is actually the requirement of HPC facility for research work. So out of 100%, only 8% say no, but the rest is really need for the HPC usage. And then this is the estimated data size for research purposes. For the highest is actually more than 50 GB. And this is the possible benefit. So we just asked, so what is they expecting? So most of them voted for the accessibility to higher computational processes, because this is actually the reason: accessibility to larger data set, larger memory size, and time saving. Because the current problem is, for example, from the bioinformatics, they have to run for like a week. So this is, I believe, like the common problems, like years ago problems of not having HPC. So this is frequent software use on HPC, Python, MATLAB, GROMAX. I believe if we get more responses from bioinformatics, probably we get more example software from them. Okay, yeah. I can say that one of the challenges, if we have a stable unit of HPC, like a complete HPC, is the challenge is to change the culture of OS, because most of the non-computer science background, they preferred Windows rather than the Unix or Linux. So you can see that most of them voted for Windows as the operating system. So this is one of the things that every time we arrange workshop for HPC, so we have to educate them for the how to move around with the Unix, using the Unix operating system. So that is very important. I believe the first challenge that we have to solve. Okay, so most of the field of study, so I just want to get back on this, probably maybe some of you wondering, we do have, in 2012, we already established the HPC unit, which being managed by Institute of Mathematics, there is HPC section. But during this time, like 10 years ago, the needs or the knowledge of HPC, probably not many of research have used it. So most of them, they really know quite well how to use those HPC. So during this time, I can see 2012, 13, 14, this HPC is actually most dedicated for the academic grade, the grade computing. So, but right now, after 10 years, after 8 years, the knowledge of using HPC, the knowledge of using HPC by the non-computer science background is getting massive. So the need is getting massive from the UPM researcher itself. So that's why they keep on acquire for the new HPC. But yes, next slide, it shows what the options that we have done to solve this problem. So this is some of the field of study that demands HPC in UPM. AI, especially about informatics, which I work with them right now. So, like most of the budget is not that much, around 100,000, 200,000. So you can imagine how big the HPC that we can get with 100,000 ringgit to 200,000 ringgit Malaysia. It's not that big, probably like one piece or two pieces of server, but probably is enough to start with, because right now bioinformatics, the institute, they don't really have their own HPC. So the practice to have HPC in one center of UPM is not really manageable yet, okay? So this is actually the rest of the field of study, computational chemistry. So UPM, originally the University Putra Malaysia, the P before this is actually for pertanian. Pertanian is agriculture. So one of our objective is to boost the agriculture using the computer science, the IoT technology. Okay. So current effort or options for HPC in UPM, first, of course, we keep on asking from the university budget. And we also send a proposal to 12 Malaysia Plan for 21 to 2025. So if we get also is actually in 2024, then we will know whether we will get it or not. But it worth to try because the budget is quite big. And most of them is actually get the options for HPC using from the cloud services. They pay the services. And for bioinformatics, they send the data to process to the company. They pay around 20,000, 30,000 for processing data. And we also did some collaborations with university and institute, for example, with this Asi Connect project, so the new one. And we also joined the TCPP so we can share. This is for teaching purposes for the CEDAR cluster. So this is how we try to get some options and also purchase like a high performance desktop using our grant money, while to how to get some options for the HPC currently in UPM. Okay, so yes, I believe that's all from me. I hope you get something from my explanation for the current HPC in Malaysia and UPM. Okay, thank you.
Thank you for Asilah. Does there anybody the question out there? Okay, and we go next. Kihyeon there.
Yeah. Are you hear me?
Okay, I can hear you, and go ahead with your presentation.
Okay. Hello everyone. My name is Kihyeon Kim. I work at KISTI. I'm in charge of development platform in KIRP and Asia Connect project. Today, I will explain platform developed in KIRP. I will explain about the Korea research platform. Our platform is based on PRP Nautilus system. KIRP is an infrastructure for research and educational institutions to carry out scientific research in various fields. Through KIRP, convergence of national science and technology can be achieved. KIRP consists of two components. Components are data network system and AI platform integration system. Data network system consists the network infrastructure that safe on security aspect and transmit big data without packet loss using DTN technology. AI platform integration system is combination function that process GPU, computing, and AI programming. It is an infrastructure built using Science DMG. Currently, a total of 8 institutions have DTN installed, and they installed Kubernetes. These servers include one Kubernetes cluster. A container-based computing environment is provided. Looking at the overall computing resources, the GPU consists of 19, and the CPU is about 400 cores. You have seen the status of infrastructure construction so far. We should develop KIRP. This platform is all configured using open sources, and a web UI is developed and provided to user to use the open source installed based on Kubernetes in an integrated way. This system is configured so that only authorized users can utilize computing. It can be used only with the permission of the administrator. There are open source for composing the KIRP platform based on containers, and it is divided into open source for composing images on the platform. As systems for platform management, there are Kubernetes, SAP, Harbor, Grafana, and Prometheus, and these open sources operate as important systems. The open source tool used as the container image in this system is Jupyter, and various machine learning interface is MPI, TensorFlow, PyTorch, R, and so on. These interfaces using Jupyter's UI and the CLI can be used. The structure of the AI research environment providing platform is as follows. The most important role among each component is by far the Kubernetes cluster module, and through this module, all functions are developed to operate on a container basis. From the user's point of view in this infrastructure, it consists of login, computing, transfer, storage, and monitoring. The transfer part is transmitted using DTN, and the login is configured to log in through the ID federation system developed by KISTI. And I will explain in more detail about other components. First, let's talk about the computing module. The computing module is divided into two parts. It is divided into individual computing environment and the distributed computing environment. The individual computing environment is configured so that individual users are allocated the computing resources they want to create a container, and the created container image is created based on Jupyter Notebook. Other computing environment is distributed computing. Our system built distributed resource environment. So we wanted to use all of our computing resources, and so thought about how we could use them. So Kubeflow is free and open source machine learning platform designed to enable using machine learning pipelines to orchestrate complicated workflows running on Kubernetes. Kubeflow provides various frameworks for constructing researchers' machine learning models. The purpose of Kubeflow in this module is for distributed computing. Kubeflow provides distributed computing environment. Distributed computing environment provides massive computing using all GPUs in worker node. Next, in order to perform the computing module, we need a system for storing images. Harbor is a tool for private image registries. In our system, it is used to provide images in private and public environments. Harbor is open source similar to Docker Hub. Harbor uses the Docker registry internally and additionally provides RBAC, web page, and image scan functions. In the case of private images, users store the images they create in Harbor, and the provided system provides an environment where users can share them according to the user's permission. Yeah, Harbor is not an external service, but a system that is installed in the internal system and can be used by applying internal security policies. Next is the storage module. The storage module consists of SEP and Loop. SEP storage is an open source software-defined software platform that make it easy to manage storage servers with software. It provides object storage, block storage, and file system interface. This size of the currently provided storage server is about 250 terabyte, and when configuring the storage, it is configured as object storage. Next is the monitoring module. The monitoring module used Prometheus and Grafana. By using the Kubernetes Resource Monitoring API, the resource information of all DTN servers is sent to Prometheus to collect index values. Using the collected values, Prometheus composes the web UI and displays it in graph form. Yeah. Next, we conducted some project based on KRP. First is Asilah Connect project. Second is developing big data and AI model management platform in the agriculture area. This picture is for the establishment of Science DMG in Asilah Connect project. This project establishes Science DMG in Korea, Australia, Pakistan, and Malaysia, and connects distributed DTNs in Asia to establish Science DMG. After that, the API platform is developed using the DTN built in each country. This platform seems like KRP. As a project to have AI research in Pakistan and Malaysia, this platform will expand and we will continue to work hard so that many researchers can use it for AI research. This project is a platform for managing and implementing AI models and big data in the agriculture field. Image registry store data and models based on images, and agriculture researchers use this platform to provide machine learning research to farmers. Farmers are provided with crop implement information or shipped crop forecast values that they want to check on their mobile phones. This platform is also developed based on KIP platform, and this is the part we will develop. Next, I prepared the KIP demo. So I show the video. Yeah. Our portal system is being renewed, almost complete. The service will start in September. We are currently checking all the institutions' modules of testing. So I hope you know that I haven't connected all the nodes. So I started video. This is the first login screen of KRP. After login, the following dashboard will appear. Yeah, the top left of the dashboard are notice, and the top middle is Q&A, and the top right is the sum of the number of organization and users. And the current graph shows the total resource usage of the node. It shows the status of CPU, GPU, memory, and disk. The map below is a world map showing where your nodes are located. Currently, all servers are located in Daejeon, so only 7 are displayed in Daejeon. The UI on the right is a system that can receive message from the administrator. Next, let's create a container. Click the Create Container button. Enter a container name. Select a container image. Select the desired resource. And select your storage. When the status of the container created in this way changes from pending to running, it can be used. As for the interface, the UI of the CLI window and the image is created if you execute the command inside the CLI. For security reasons, commands with administrator privileges cannot be executed. If you select a Jupyter image and access the UI, it is as follows. You can develop an AI model you want and perform various tasks using the following UI. Because Jupyter Notebook provides an interactive interface, you can check the result of each function immediately. And then this button is a file browser. You can upload, delete, and download data in my computer as follows. This button is the monitoring button. In this case, the path monitoring system. You can check the CPU, memory, storage, and network usage of the path you are using. Next is the storage management menu. There is a default storage for each user, and additional storage can be created if needed. When storage is created as follows, and data can be uploaded, deleted, or downloaded by opening the file browser of the Create Container menu in the same way. This information shown below is information that can be shared between other users using S3. And using this information, it is possible to link with other clouds through authentication. The following this menu where you can check the status of a node. You can check the CPU, GPU, memory, storage, information of the nodes configured as follows. And then the next menu is the Globus Online menu. And it consists of an environment where users who have connected to Cafe can automatically connect to my Globus and send data immediately. The demo is over. Thank you for watching my demo. Thank you.
Okay. Thank you for your presentation. And we don't have much time, and we have 2 topics remain. And I want to skip this question. And Asif, are you there?
Yeah, I am here.
Okay, go ahead. Your presentation.
Can you please stop the share?
Yeah.
Okay, can you see my screen?
Yes, sir. Okay, go ahead.
Okay, hello everyone, and thank you, Dr. Moon, for giving me the opportunity to present the network status of our project, Asia Connect project. And in this presentation, basically, I'm going to present about the network connectivity of our project, building a distributed HPC platform, right? So these are the contents that I am going to cover in this presentation. First of all, Dr. Moon already gave you the overview of our project and the 3 activities that we are going to do. But in this project, I'm going to focus and emphasize on the activity 1, which is basically related to the interconnection of the participating countries and installation of the DTNs and deploying the monitoring system, such as for science DMZ monitoring and DTN monitoring, and finally the conclusion. So let's start with the first activity. As you know, this is basically our proposed distributed HPC platform that we are going to develop in this project, right? But when we talk about this project, we discuss about these 3 activities that we have to accomplish, right? First activity is building a big data superhighway based on the TEIN networks. So as I said, in this project, this activity will be, in this presentation, this activity will be more focused, and we further subdivided this first activity in what we do in this activity. Basically, here we mainly, use the TEIN infrastructure, IT infrastructure for the Asian underdeveloped countries and developing countries, such as the Malaysia and Pakistan, and connect with the some developed countries such as the Australia and Korea. And in this activity, we interconnect the local, national research and education network partners from all of these countries and establish a big data superhighway. So we have to link the NERNs, and we have to link the DTNs, also DTNs, because we want to establish the high performance computing environment here. So by using the DTNs, we will share the resources, and also we establish the science DMZ environment on all these, participating institutions, and finally to monitor the all these institutions. And so this is basically the picture when we connected. Final picture will be look like this when we completed this activity. So almost this activity has been completed, and we connected the 4 our participating institutions. But I will explain that what network challenges that we faced and how we connected, how we tested all these things. So because when we try to connect all these, multiple countries together and build a distributed environment, so definitely the first and foremost, challenge that we have is basically the network challenges. So here I will discuss some network challenges in first part when we talk about the interconnecting the NERNs via the TEIN network. So I will discuss about challenges. Here you can see this is a map of TEIN, right? So in this TEIN map, you can see all the participating institutes. Pakistan, Malaysia, Korea, and Australia are there. They are connected with different links, with different routes. So what are the basic challenges here that we faced when we were trying to connect all these participating countries? Basically, if we look there from Pakistan to Korea, if we have to connect these 2 countries, then there are lots of routes are available from Pakistan to Korea. So first challenge is optimizing the routes from 2 countries, among all these countries. So first challenge that we faced is basically related to that. And the second one is basically to optimize the routing among these countries. So this was the ultimate goal that we have. our ultimate goal was to optimize an independent and dedicated end-to-end paths. Means end-to-end means from Pakistan's institute. Whose mics is open? I think I'm getting echo. Okay, thank you. So if we talk about, can you please turn off your mics because I'm getting echo. Okay, thank you. So when we talk about the challenges in Pakistan, we are not only, connected here as an end host, because end host is your institution. We have institution as Sukkur IBA University, so we have to configure end-to-end optimized independent dedicated paths in this network. So these were the big challenges. So we divided this activity to connection activity in these three phases. First, we analyzed and select the path, that which path we should have to follow in this TEIN network map, and how we can assign the IP addresses to our end host, means our DTNs, and then how we can test the interconnectivity. So I will explain one by one. In phase one, we basically selected this path from, let's suppose all the participating institutions are here. You can see Pakistan, Malaysia, and Australia. So we selected this path because this is a most optimized and independent, and you can say most relevant path for all these institutions, and maximum bandwidth is also available for end-to-end connectivity. This is the first phase in which we analyze the path and we select the path. In the second phase, we assign the IP addresses, and I would also like to thank all the participating institutes, co-PIs and PIs, because they collaborate with the local NERNs. Local RENs means the National Research Education Networks. From KISTI, we contacted with the KoreaNet. From NCI, Andrew was contacting with their RNet, and from Sukkur IBA, I was contacting with the PAN, and from Malaysia, Dr. Asilah and Dr. Asif was contacting with the MyREN. So they got the IP addresses for their end host, for their end DTN, IP pools, and they assigned the IP pools to their DTNs. And once we assigned the IP address, then we tested the path. We tested the path from the Pakistan to Korea. So here you can see the trace route result are showing here, and you can see it is going via the PAN and then Singapore and Hong Kong and South Korea and KISTI. So as we decided previously in the first phase, that path is now, we are utilizing bidirectional path, and our traffic is going and coming back from between the DTNs. So we can see the ping time is around 165 milliseconds, and Aprp results here you can see between the DTN node at the Pakistan and the Korea, we can achieve around 734 megabits per second. Although we have between Pakistan and Korea, we have 2.5 G maximum bandwidth is available, but because of end host having only 1 Gbps link, therefore we are getting this limited bandwidth. So at least we are achieving more than 70% total bandwidth here. Similarly, we tested between the Malaysia, and same path that we decided before, we are utilizing that path here, and around time that we can see in ping results 119 milliseconds, and the total bandwidth is similar like that Pakistan we have with the Pakistan that we achieved before. So between the Malaysia and Korea, we can achieve the bandwidth of around 743 megabits per second. Same thing here also, because our end host is connected with the 1 Gbps link. So these three activities we perform, and we connected our end-to-end DTN nodes on this by using the TEIN network. So in this activity, basically we face lots of problems, and a last mile problem, and local NANs problems, and also problems on the international NANs, definitely, and some related to the firewalling issues also we faced in this connectivity. The next phase is the installation of DTNs. Once we connected the DTN, then we install the DTNs. Currently we don't have the hardware provided by the TEIN because it is in progress, and we will receive the DTN nodes and other hardware for all institutions. So we temporarily arrange the DTNs at the participating institutions at Sukkur IBA University in Pakistan and UPM in Malaysia. And thanks for the their collaboration and cooperation. Then we install the specialized DTN servers with advanced science DMZ architecture. I will discuss later on, and that we tune the networks and operating system of these DTN nodes, and then we design the uniform security policy also for these institutions, that how you can deploy science DMZ infrastructure here. This is the overall picture of after installation of the DTNs at the participating institutions. You can see we have the IP addresses, all the DTNs are connected, and we have science DMZ, environment architecture. So this is like a science DMZ architecture where we are separating the institution and the research network. So here your DTN is separated in this science DMZ architecture. This is not yet completely deployed, but partially we deployed at the Sukkur IBA University, and we will deploy on other participating institutions in future, because we currently design the policy, how we will deploy. We deploy the security policy. In that security policy, basically what we are doing, we are allowing the traffic of related to the Kubernetes and perf sonar. And these policies will be deployed on the end host and DTN host and the relevant switches or routers that are that will be connect the DTNs directly. So we will minimize the security policy. So this is basically the security policy that we will implement in future. And also on these DTN nodes, we tune the network, TCP tuning we did here to achieve the maximum performance between the nodes. And after that, after installation the DTN and connection of the DTN, then we deploy the monitoring system. So this is basically how we deploy the monitoring system in our premises. We have four DTN nodes, temporary DTN nodes available on every site. Means the KISTI, Australia, Pakistan, and Malaysia. So we deployed the perf sonar test points here in the form of Docker. So you can see all the Docker images are running here in KISTI, Australia, Pakistan, and Malaysia. And these are sending the some statistics of connectivity, performance, loss, total bandwidth, total path available. So all these statistics are sending to a central node which is located in KISTI. If you can see in previous slide, this node is a med-dash node which is located in KISTI, and all these DTNs are running the Docker images for perf sonar test points. And here you can see end-to-end connectivity we can monitor by using that test point, perf sonar test point. So that test point is sending the statistics to this med-dash node. So here you can see all the nodes you can see are connected. Pakistan node, Myren node, and the Australia node and other KISTI nodes are connected here. So gradually, once we have the science DMZ architecture, once we implement the security policy, and then we can see that all these boxes will be in green in future. So this is what we did in monitoring system. And if I conclude my presentation, then I can say that network connectivity has been completed with participating institutes, and we utilize the TEIN network, but we need to optimize more optimization at the network level, at the OS level, to achieve the more better performance among these institutions at the network level and operating system level. Although, as I said, we temporarily install the DTNs at every institution, and we have some science DMZ architecture, limited science DMZ architecture there. In future, we will replace this hardware, existing hardware, with the new DTNs, dedicated hardware. and switches, high performance switches. And also we will apply the science DMZ security policy in that form that I described before. And also measuring the science DMZ using the monitoring system, we deployed using the Kubernetes monitoring system and the performance of to achieve the performance of the end-to-end DTNs. So this is all about the right now our activity. One of our project has been completed, and we connected the participating institutions from other countries, and we build you can say Kubernetes you can say the environment by connecting the DTNs, and we tested, we installed the DTNs. So now all the DTNs are connected, and next step that is basically is related to the deployment of actual platform. And it is also partially done, as discussed before by the Dr. Moon, that our platform is partially done, and we are moving ahead. And this is all about my presentation. In next presentation, I will discuss more about the pilot projects that we are trying to deploy at Sukkur IBA University. Thank you very much. If you have any question related to the connectivity, please let me know.
Asif, is keep going to your next presentation.
Okay. Sorry. Can you see presentation?
Yes, sir.
Okay, thank you.
Yes,
please
go ahead. Make it short.
Yeah. Turn off your mic, please. Okay. Again, thank you very much for giving me opportunity to present the Pakistan country's updates, basically related to the AI science. Because being a co-PI of this project, we have to work on AI science use cases. So again, if I talk about our distributed platform for AI science use cases, it is ready. And we utilize this platform from Pakistan to demonstrate the real use cases that we can implement. So I will explain in this presentation that how we can how Pakistan and Sukkur IBA University is basically utilize this platform in future and demonstrate some working use case that we did in this platform, current Asia Connect platform that we did. As you know, this is basically our part where we have to work on the use cases related to the AI science, and we have to enhance the algorithm. We have to demonstrate the deep learning, machine learning algorithm, and also we have to demonstrate the big data transfer in this platform. So if I talk about our roadmap at Sukkur IBA University in Pakistan, we have here, we are basically promoting the AI research at Sukkur IBA University in two ways. Our first way is basically to promote the AI research by using our department, which is a computer science department here at Sukkur IBA University. Here we are teaching the courses, different type of courses which is relevant to the AI at the undergraduate level and the graduate level programs in BS and MS program. We teach the courses of AI, machine learning, deep learning, reinforcement learning, computer vision, and data science, and NLP, and etc. in computer science department. So normally here our students are engaged with the teacher, and teacher is basically the teaching using some methodologies to teach the AI and promote the AI research here locally in Pakistan. The second, our part which is promoting the research in AI is basically our lab, which is called the CRAB lab. That is basically the center of excellence for robotics, AI, and blockchain. About the CRAB lab, more details about our projects and CRAB will be discussed in next session by the Dr. Ghulam Mujtaba. And this basically CRAB lab, how we are promoting our research in this CRAB lab, we conduct some training from outside for outsiders or for students or some other professionals related to the AI, machine learning, and deep learning. We also conduct some workshops related to the AI, machine learning, and deep learning, and also we conduct the seminars. So these are the two parts in Sukkur IBA University in Pakistan which are trying to promote the research related to the AI. So now the question is that how we will utilize this platform that is currently available. We are going to deploy among these countries, that how we will deploy, how we will utilize this platform for Sukkur IBA University in Pakistan, particularly for AI research. This platform will be utilized in this way. First, whenever any teacher is going to teach the courses in the class, they can utilize the platform to teach the students in classes that how you can do the AI research by using this platform. And second part, we can promote or we can utilize this platform by using the AI research trainings, because in KREB, I said we are giving trainings to some professionals, some researchers, some students in KREB lab. So we can utilize this platform for that purposes. And also we can conduct some workshops, AI workshops, by using this platform. And also we can conduct some seminars where we can demonstrate some distributed training, distributed model learning, and all these things by using this platform. So this is basically how here at Sukkur IBA University we are planning to utilize the distributed HPC platform for AI research. And these are the distributed training frameworks that we are targeting to run on this distributed platform, such as PyTorch, distributed TensorFlow, Harrowwood. These all are the well-known, well popular and mostly usable platform nowadays, distributed platform nowadays for training in AI research. PyTorch is most popular deep learning framework which is developed by the Facebook, and it is more easy to use and flexible, as well as the distributed TensorFlow, which is developed by the Google, and it supports the distributed training as well as by using the Keras APIs. Harrowwood also, it's recently developed in 2017 by Uber, and it support all the major platforms, major frameworks like PyTorch, TensorFlow, Keras, and MXNet, and all these things. So on top of these, you can run distributed training by using the Harrowwood. So these platforms, these frameworks, we will utilize in our this platform. And these are the some algorithms that we will use for AI science use cases in future, DNN, RNN, neural networks. Because when we talk about distributed training, it means we are dealing with the neural network, mostly deep learning, right? So we will utilize these algorithms, all these algorithms, reinforcement algorithms, variational autoencoder, and MCMC algorithms, SVM. So these algorithms we will try to, as a use case, we will try to run on this distributed environment. So right now, we utilize this platform, we access this platform currently developed, which is currently developed by the Kihyeon Kim, and he gave us the access, and we demonstrate some TensorFlow example in this platform and the MPI example in this platform, as discussed before by the Dr. Moon as well. So in this video, just I would like to demonstrate a simple distributed training of MNIST, and here you can see how we utilize the platform for distributed training from Sukkur IBA University, right? This is basically our main cluster. I'm accessing the main cluster. I will explain one by one. I'm accessing the main cluster, and you can see in this cluster our distributed platform, all the nodes from here. You can see all the nodes are working, right? All these nodes are working in a cluster, And in this cluster, I will, execute the distributed training by using the MNIST. And if I see the pods, you can see all the pods are running, our safe storage running, our Kubeflow modules are running, and complete our environment is ready for use, right? Now I will, next I will show you the which example that I'm going to execute. This is a distmain.py, is a Python file in which we write the code, and we utilize the distributed training by using this HPC distributed HPC platform. So this is the code of our file, which we are utilizing to run in a distributed way. Basically, it will distribute it among all the nodes which is available in our cluster, Kubernetes cluster. And this is basically the file that YAML file that we are using, the TensorFlow operator. And I created my own image in which I execute the said file. And here we define one parameter server and two worker server. Parameter server, worker server will communicate with the parameter server to share the gradients. And I assign the two CPUs. Initially, I assigned the two CPUs to worker nodes because we want to first test with the CPUs, and then we want to test with the GPUs, and we will see what is the difference in this distributed training and how we can achieve the better performance by using the CPUs and GPUs. So I'm going to run the that YAML file now. I apply here simply the test job, and it is started. You can see it's created. And if we see the logs of the pods, our pods, so we will see this these pods are started running. One our PS parameter server, and two our worker nodes are running. One is running on Malaysia node, another is running on Pakistan node, right? So here you can see when we see the logs, it will show you the outputs of the running. This is a parameter server which is listening the workers from the ports 2222. And here you can see if we start watching the logs of worker node, then you can see training is ongoing, right? Here you can see training is running, and when training will be completed, it will show the complete simulation time and all these things here after completion of the training, right? So here, once the training will be completed, we can see the overall time, because it is using the CPU, therefore it is very slow, right? Once we change into the GPU, it will increase the performance, distributed training performance. So currently we are running with the GPU, and here you can see it's going to be done in few seconds. Yeah, training is now completed, and you can see the logs. If I see the logs of my training, you can see it's taking around 160 seconds total time for training this job in a distributed way by using the CPUs, right? The next thing that I would like to explain, that now we are going to change the from CPUs to GPUs, because we want to increase the performance of our distributed learning here. So first we deleted, and then we change the settings here. Now I'm going to change the settings here. You can see I will change the settings of here you can see I'm going to utilize the GPU, NVIDIA GPU, for my worker nodes, not for my parameter server, because if we run parameter server on CPUs, it's okay. But worker nodes are mainly, working in a distributed way. Same two workers, and I'm utilizing the one GPU for per worker node. And if I run the job again, you can see job is started and it's running. And here it's running, it's creating the container and it's running, right? And if we watch, it's running all, jobs running again with the GPU. Now we are running with the GPU. Previously, it took around 160 seconds to complete the job. Now job is completed. If we see the results, you can see if we see the results here, you can see it's taking total around 41 seconds only, because we now utilize the GPU in a distributed way. So that's all about this example that I want to show you here. Basically, in this example, what we did, we utilized the distributed HPC platform, and we executed a distributed TensorFlow job, where first we executed the TensorFlow job with the CPUs on 2 nodes, which is located in, you can say, in Pakistan, or you can say in Malaysia. So then same job we executed on GPU, and we can see the performance difference here among the both results, right? This is what I want to show in this use case. I have another use case which is related to MPI, but I think its time is over, so I cannot explain about, because it's almost to take more 7 to 8 minutes. So thank you very much, and if you have any question, you can ask.
Okay, thank you, Asif. We had this 20 minutes to pass. Thank you for that. And sorry for that. We the 20 minutes passed. And I wanted to make up this session. And thank you for attending and joining. And 10 minutes later, and we started the tour. And at the time, it's a technical, it's announced after 10 minutes. See you session 2. Bye. Thank you again.
Thank you, everyone.
conference meeting. It was held in Trieste in Italy, and it was really great to catch up with a whole lot of my colleagues again after 2 years of no travel. There were quite a number of really interesting presentations at TNC. However, I think I'll just give you kind of a general view of the conference. A lot of great keynote sessions, particularly in the area of applied medicine, and a whole lot of sessions on social interaction. So I'll just switch my presentation over to my other slide deck, if you just give me a moment. Okay, I'd like to start by acknowledging and celebrating the first Australians on whose traditional lands we meet, and pay our respects to elders past, present, and emerging. So I'd like to really focus on some of the new capabilities and interfaces that we've been building on top of our Niren Cloud. Our Niren Cloud occupies around 22 racks. As you've heard from some of our previous presenters in the last session, we're participating in the Asia Pacific Research Platform, and we're running some of those capabilities on a Niren Cloud. The Niren Cloud is built on some fairly old technology, Sandy Bridge and Broadwell level. So we've been undertaking a technology refresh to progressively update a number of the internal infrastructure capabilities. And we're now looking at updating our compute capabilities by adding additional GPUs and more current generation CPUs. As Asif mentioned in his presentation, AI training and machine learning is a growing part of our portfolio. And there's quite a significant interest in us expanding those capabilities. I'd also like to discuss some of the activities we've been doing in terms of rolling out what we're calling the Australian Research Environment, or ARE, and then conclude with some updates on our soft iron storage that we've recently installed. So our Niren Cloud, Niren is the word for the edge in the Australian First Nations Wiradjuri language. Our Niren Cloud operates as an infrastructure as a service platform based on OpenStack, which allows us to deliver edge case services which fit alongside and support our traditional HPC capabilities. Niren is used both internally by NCI for service delivery and for our stakeholders to deliver both long-running and web service applications, and things like Galaxy for genomic processing and workflows. So our Niren Cloud is, as I mentioned, OpenStack based, uses about 22 racks spread across our 2 data centers. We've got about 1,500 Broadwell cores and around 42,000 Sandy Bridge cores with around 200 terabytes of memory. We've also got 4 large memory Optane nodes, which have 3.6 terabytes of memory across them. We've integrated our old K80 GPUs, but we're in the process of refreshing those to a more advanced and contemporary GPU platform. We've got around 6 petabytes of operational storage, with another 12.6 petabytes that we're preparing to bring online at the moment. As Asif also mentioned, and Kim, the Ceph is an open source storage system that supports volumes for block operations, file system using Cephfs, and S3 for object-based presentation. Something that we've done quite recently is virtualize our root partitions and actually move those to be backed by Ceph, rather than node local storage. This provides us some very significant advantages in terms of live migration and drops our live migration time from about 30 seconds down to about 2 or 3 seconds, because we just don't need to move the images. We can reattach the underlying storage behind the scenes, resulting in the maintenance being almost completely transparent to users. NIRN supports a wide range of NCI service delivery, our public-facing data services for data collections, data analytics and dashboards using Grafana, and a number of homegrown analytics platforms. We do a lot of data inflow and processing, particularly in the satellite and Earth system space. And we run a number of service portals, including virtual laboratories and research environments. NCI supports NIRN stakeholders, NIRN supports NCI stakeholders as the delivery platform for many of the applications and services used over a complete range of science disciplines at NCI. Our infrastructure as a service offering allows our stakeholders to dynamically configure the compute and operational environments that they wish with security groups, and it can be scaled up and down to meet their requirements as needed. Something that we've introduced in the last 6 months since the last APAN meeting is a capability called ARE, or Australian Research Environment. ARE provides a web-based interface to our Gaudi supercomputer and also onto our NIRN cloud. This significantly lowers the barrier to entry for new HPC users, while still providing the flexibility our advanced HPC users expect. We've incorporated the best aspects of our virtual laboratory into an application-rich set of discipline-specific tools with workflows optimized for our users' needs, and so that they perform well across a range of NCI platforms. That underlying work, while not particularly glamorous, is really, really essential to optimize different tools and applications for different CPU architectures, different GPU architectures. So we're able to select the most appropriate platform for any particular user's needs. ARE is based on the Open On Demand platform created by the Ohio Supercomputer Center. If you'd like to look at Open On Demand, the link is there, openondemand.org. It provides a GUI interface to traditional HPC applications and graphical applications. And one of the key things is that it doesn't require any software installation to be performed on your local workstation. You can just access it using a web-based interface. We're using traditional X applications. It provides a SSH login capability and integrates with Globus, which is our national platform for data transfer. So users are able, with a single click or a drag and drop, to move data around facilities in Australia and longer term across things like the Asia Pacific Research Platform. So ARE is web-based, based on Open On Demand, no local software installation needed. You access it via are.nci.org. It provides a really easy to use graphical front end for applications. We've added most of the commonly used graphical applications and are increasing the portfolio of applications. We've been using Jupyter Labs for training, and ARE has become an essential part of our NCI training portfolio. So you can see just a few screenshots of ARE, and we're able to add additional applications or package up our HPC applications, which are supported using the module system, which is commonly used in HPC environments. So I'm just showing you a couple of the screenshots as we move along. what we've been using ARE for is one of the first trial test case uses was our satellite data workflows, where we perform geo-rectification, cloud removal, color and light adjustment, and then they're added into the Digital Earth Australia data cube for longitudinal and transectional retrieval. So for an example is you can retrieve all of the data in a polygon that we've captured over the last 20 years of satellite data and perform a longitudinal and transectional analysis through that. We've used that to plot water flow changes and perform analysis of river system functions in Australia. So NCI is about combinative science, bringing together data from satellites, telescopes, sensors and Internet of Things, ultra-high definition images, genome sequences, and external data sources from all around the world. As I mentioned, we tightly couple HPC, cloud, and data, which is NCI's unique selling point. And just to close off, we've recently installed another 12.6 petabytes of Ceph storage, which is based on a platform called SoftIron. That's going to be used to do a lot of data reprocessing and also augment our S3 and object-based storage capabilities in NCI. So we exist in a globally well-connected world, and I'd like to thank all of you for participating in APRP. And we value your contributions very much going forward. So that about wraps it up for my time. If you have any questions, please feel free to contact me, either on chat here on our APAN Slack or via email. So thank you very much, everyone. And with that, I'll open it up to questions if anyone has any. Or if not, we'll pass over to our next speaker. Do we have any questions from anyone? Okay, well, in that case, let's, with our time being very short, pass over to our next speaker, who is Michael Vetz from SurfNet in the Netherlands, who will be talking to us about expanding research platforms with public clouds. Over to you, Michael.
Good morning, Andrew. Good morning, everybody. Thank you for having me. I'll speak a little bit about our expansion of our own infrastructure with public clouds. Those who don't know you, me. I'm Michel Vetz. I work at SURF. SURF is a Dutch NLAN. We service vocational higher education, universities of applied science, research institutions. And I have about 3 hats on there. One of them is I lead the cloud team. I'm responsible for the cloud services. And I'm part of the JL procurement platform. So we try to help NLANs in Europe with cloud services. And well, for those who don't know where the Netherlands is, that's where we are. It's a really tiny country, nothing like Australia. It's about 300 by 200 kilometers. But we have about 17 million people. And SURF has been growing quite a lot recently. We've accumulated merged 3 working organizations into SURF. And that now gives us an organization who is not only got to do with the traditional NLAN stuff like network connectivity and middle layers, but also deals with an HPC. We've got our own HPC supercomputer and services which we deliver. So yeah, moving, there you are. I'll start with the public clouds part. So the great thing we have in Europe, which is a burden sometimes too, is that we have a common procurement legislation across the European Union, and that allowed us to run a single procurement for cloud services, and that deals with about 40 countries and 10,000 institutions. So by running a single procurement, we give access to all these institutions on research and education to use cloud services without having to tend them themselves. And that gave us a broad set of all the US hyperscalers, Microsoft, Amazon, Google, Oracle, IBM, but also a broad set of European suppliers, recognizing that some institutions, some researchers prefer not to have the data go to the US as the privacy concerns. And this broad set gives us a really good tools to do transformation. And what we've done in the Netherlands is that we've got a dedicated cloud team. So we've got our own advisors, 3 of them helping the institutions with making the choice, because our biggest value is being the trusted advisor. Basically, we have one KPI, the customer satisfaction. It doesn't matter to us if an institution chooses to use a Dutch, a European, or an American cloud supplier. It is about their functional requirements, and if they are met best by one supplier, that is the one they should go for. So we give ample possibilities to create communities on technology or on maturity of cloud adoption, and by doing so, we've become the default for cloud delivery in the Netherlands, based on these European procurements. Excuse me. The research usage there has been growing. It's about 10% currently, and we see that growing further. To give you an idea of this is the institutions using cloud services, and this is predominantly central IT, right? This is not just research. I mean, the research university institutions and universities, yes, they use it for research too, but a lot of it is central IT, about 90% of the consumption, and that is about 26 million euros this year. But over 90% of our members use cloud services, and the NREN has a real possibility to provide to become the trusted advisor there to help them, because a lot of them do find cloud services quite difficult. So that's the public cloud services. Service and NREN traditionally also has a lot of its own compute facilities. So we have a supercomputer, refreshed 2 years ago, Snellius, still ranking highly in the world ranks. We have an HPC cluster, and both of them are governed by the Dutch Research Council, so researchers can do free computations there. And we also have a cloud management portal there, which scales out to some public cloud services with SaaS services, Jupyter notebooks, that kind of stuff, and connects those. So we've seen a lot of NRENs who've invested quite heavily in their own hardware, and who are struggling with, okay, should we have researchers use our platform, which is paid for and which we operate, or use also public cloud services? We believe that choice is not necessary. We believe in giving the researchers a choice of what platforms they use, because we see it increasingly happening that they would rather do it in public clouds because of time restraints. For instance, a study ordered by the Dutch government on the impact of environmental changes, which has a deadline to be met. We see that sometimes functionalities are not always available locally. For instance, there's not enough GPUs on the local or on the server infrastructure to run certain things, or machine learning algorithms learned services are not available locally. We also see that there are international collaborations where the consortium has chosen a cloud supplier, and it's easier for everybody to use that. And another thing is scalability. Sometimes there are just jobs which are designed or which intrinsically much better would perform on a public cloud service. So what we're going to be doing is a proof of concept where we start by looking at a single job on our supercomputer or HPC and see how easy it is to migrate that and run that on initially Azure, AWS, and GCP, Google. Because for researchers to understand the choice they have, they should know how difficult it is and what the benefits may be. So we will look at how easy was it to transfer the data, recognizing that not all suppliers have as good connections to serve. How much rewriting, recoding was necessary, how long it took, what did we encounter for problems, and how much does it cost? And the outcome of that should give the researchers the understanding of the ease or maybe difficulties to run it on a public cloud. And these first 3 suppliers are chosen because there are the big ones out there. But if this is successful, we will also do this to look at, okay, so how about using the resources in another university if they're spare? How about using the HPC in Germany through DFN? How about using the European cloud providers? So we aim to give researchers a broad overview of what's out there and how easy it would be for them to move a job or to run a job elsewhere if that makes sense because of the functionalities or the resources or the time constraints they have. So this is something we're trying to do as SURF to help the institutions with their choices, and not just offer our own infrastructure or only offer public clouds. We believe that there will be reasons why researchers run jobs on their local infrastructure for whatever reason. It may be on a community cloud, and it may also be on a public cloud. And it is our role, we believe, to make that transparent for them and to help them along the way. So I kept it brief. I do hope you got some questions.
Thanks, Mikael. I've got a question if nobody else does. Is that report going to be available beyond the European community?
Of course, because we all collaborate. Sure, yes.
It would be great to hear some of the results of that because I think we're looking at similar things.
Yeah.
So excellent work. Thank you very much. Any other questions for Mikael? Okay, so our next presenter is Asif again from Perdana University, who will be providing the ASEAN update. Over to you, Asif.
Thank you, Howard. I must apologize. I'm surrounded by nature. I'm on vacation, so you'll hear rooster sounds and tourists. So I'll keep it short. Hopefully you can still hear me, but I try to find time to actually give this presentation. Okay, so very quickly, so I want to give an update on the ASEAN and HPC for bioscience. And so let me just begin. Okay, so very quick, actually this is less of an update, more of an overview for those who are not familiar about the Aprp and its history. So we kind of started with this group in 2018 when we had our first meeting in Singapore, APAN 45. I'm actually surprised to see that we have hit the 10th meeting milestone. And so congratulations to the team, Jeonghoon, Howard, and others who have managed to have this year twice a year since 2018, and we have made some progress over the years. So there was a bit of a history. In 2018, when we started, we were quite fortunate to have funding from TEIN, and we were able to actually bring together various key opinion leaders from ASEAN. And as a result, we were able to kickstart this effort. These are the names of the people. Unfortunately, since then, we were not successful in bringing all these people together. Of course, Corona then happened, so that also affected. But nonetheless, the conversation has been ongoing and progress is being made. The key motivation, I'm not going to go into the basics of HPC, which you all are familiar with, but the really key objective of APRP is to promote a vibrant and relevant HPC ecosystem in ASEAN or among ASEAN countries. You hear the rooster? Okay. So these are some of the updates that I've gotten from people that I spoke to. So the effort, led by the ASEAN HPC Task Force was formed in 2018. And the key recommendation from that was to form a shared HPC facility. And however, this regional shared facility does not exist yet. And individual countries nonetheless already have national and local facilities. So there are local efforts, but an ASEAN coordinated shared facility is not available as of now. Dr. Piawut Sri Chaikul, co-chair of the ASEAN HPC Task Force, had shared the following key insights about the shared facility. This is the model. They will rely on centralized or a few distributed HPCs with some type of exchanging value. Collaboration will not be restricted among just ASEAN members, but will be also open to others. And these ASEAN distributed hubs will open doorways to global HPC resources. But the key is, while these efforts are ongoing, training must be continued, preparing the people, preparing the users to be able to utilize such a resource is important, and their efforts are ongoing for that too. With regards to this, one key notable effort that has been made is that the use of Riken Center for Computational Science, which is home to the Fukagu supercomputer. So the idea is to be able to use this world-class computing infrastructure, that's being made accessible and available to the ASEAN researchers. I think there was a call, according to Professor Suhaimi, a call was made for people to submit proposals to utilize the compute. So the near-term goal is to establish this inaugural ASEAN shared facility on Fukagu, and maybe later on they might have something that's within ASEAN, but for now the idea is to use Fugaku. And this is also in relation to the training that I mentioned. There's a collaboration with the regional EU-ASEAN dialogue instrument, and this has led to this ASEAN HPC EU ASEAN HPC school. This actually has I think this is this has seen several installments. This is not the first, and there's one that's upcoming from 5th to 10 December. So if you are in ASEAN and you would like to participate, you want to check out the website down here, hpcschool.net. Separately, there's also this Hpc Ai competition that's ongoing. This is the 5th call, 2022. They had the winners of last year announced. There were quite a number of participants from ASEAN and outside ASEAN. So the current one is ongoing. It was announced in March to Supercomputing Asia, at Supercomputing Asia, and I think proposals have been closed by April. And this will be kind of, the showcase will be, I think, in November. So this is something to look out for. There are other notable HPC events, Supercomputing 22, it's going to be in the US, November 14 to 17. It's interesting that the next HPC Asia will co-locate with Supercomputing Asia and will be held in Singapore from 27 February to 2 March. Now, with regards to applications, we would like to actually invite users who then showcase how they see the use of HPC to solve real biological life science problems. So we have invited two members of my team who will be presenting later, Mohammed and Ezra. They'll be sharing their case studies later, so look out for those two talks. And this is part of an effort that's funded by Asia Connect. The title of that proposal that has been awarded is Building a High Bandwidth Distributed HPC. And this is for 12 months with 150K euro support from Asia Connect. And I want to congratulate Asif Raza, who presented actually the work at the 2022 International Conference on Platform Technology and Service, PlatCon 22, and he got the Best Paper Award as part of that presentation. So congratulations to the team. And this is a reflection of the importance and timeliness of the work that's being done. And hopefully this would allow better connectivity for those ASEAN member countries and users to take advantage of such a facility to solve really complex biological problems. So I'm not going to present the case studies. Usually I do that, but today I'll have members of my team, Ezra and Mohammed, will be doing that later. So I just want to end that hopefully, you know, as a member of the ASEAN country from Singapore, I really look forward to such a facility. I think Fugaku is a great start, and I hope more to come, more to see towards this, and so that you know, there are really people who need such kind of facility. In fact, now I'm actually based in Turkey at the moment, and we really see the need for such facility. Even doing docking, I mean, MD stimulation, you are delayed by weeks just because you're not able to do this quickly. So more can be done, more can happen if we have this. And of course, we also need to train people to use this because it's not straightforward. So just running things on your laptop or desktop. With that, Howard, thank you very much. And again, I apologize for all the background noise. I hope this was nonetheless still informative, and do look out for the case studies from the team members.
Thank you, Asif, and very well done on that award for the paper. That was really great work. Does anyone have any questions for Asif? Okay, well, let's move on to our next presenter, GM from Sukkur IBA University in Pakistan, who will be discussing AI science status and requirements in Pakistan. Over to you, GM.
Thank you so much. Good morning to all of the participants. I am GM from Pakistan. I work in Sukkur IBA University. Today, I'll talk on AI science status and requirements in Pakistan. So this is the brief agenda of my talk. I'll quickly introduce one of the centers we established recently at Sukkur IBA University called the CRAB Center. Briefly discuss some of the projects of CRAB Center. Also, I'll discuss some of the available resources for AI applications and some current challenges we face while deploying the AI applications and our future requirements for AI projects. So recently we established this center called CRAB at Sukkur IBA University. CRAB stands for the Center of Excellence for Robotics, Artificial Intelligence, and Blockchain. So actually in this center, we had 3 different clusters, robotics, AI, and blockchain. So there are a few teams who are working on robotics application. There are teams who are working on AI applications. There are teams who are working on the blockchain applications. So the facilities which CRAB provides are the GPU-based workstations. We have uninterrupted power supply, 24/7 high-speed internet connection, humanoid robot platforms, mobile robotic platforms, soft robotic platforms. We have 3D printers and PCB machines. So these are some of the pictures of the center. So you can see the center is equipped with lot of robotic platforms, the GPU-based workstations, and so many fields there to deploy the robotic or AI applications. So these are some of the activities which we perform at CRAB Center. Okay, so the vision of CRAB is to become a world-class center of excellence in the fields of robotics, AI, and blockchain. So at CRAB, our objectives are to undertake the patentable research, to produce the skilled human resource in the fields of machine learning, deep learning, soft robotics, and blockchain applications. And the third objective is to obtain the national and international grants for AI applications and robotic applications. So mainly our AI and robotic team work on intelligent transportation systems, precision agriculture, soft robotics, speech-to-text classification systems, NLP, medical image processing, and computer vision. So we have a lot of projects, but because of the time limitation, I'll just explain, 4 current projects which we are doing for with the collaboration of industry. So these are the projects which we do with the collaboration of industry. One is aspect and emotion recognition from audio calls recorded in Urdu language. Other one will be classification of Pakistani cards to augment the Safe City project. The third is multiple object tracking for aerial view images. And the fourth one is offline handwritten text recognition. So these 4 projects we do with the industry. So this first project, which is aspect and emotion recognition from audio calls, we do this project with the collaboration of Cybrid. Cybrid is a company of Lexan Group here in Pakistan. So they had a huge, bunch of call centers available throughout the Pakistan. So this project is funded by Higher Education Commission in Cybrid, whereby we process the Urdu calls recorded in the call centers, and we try to elicit the emotions and aspects. So, for example, the client who is renting the services of call center is interested to know, the call center agents how call center agents talk to our clients. Within happy mood or sad mood or angry mood or frustrated mood. And if, for example, they are talking to our clients in happy mood, so what is the context? The client is happy because of our service, because of our product line, or so on and so forth. So in this project, actually, we aim to elicit the emotion as well as the context from the recorded Urdu calls. So this is the brief methodology we perform to elicit the emotion and context. So other project is Pakistani vehicle classification using deep learning approaches to augment the Lahore Safe City project. So in Lahore, there are around 8,000 CCTV cameras deployed to provide the safety to the citizens. And the government hired around 400 staff members to look after that control center. So the issue is those CCTV cameras can record the videos, but they are not able to query anything from the recorded videos. For example, if any car is stolen, so I cannot query them, okay, retrieve all the white, for example, Honda Civic car having model number 2018. So these things, it cannot be performed on those videos. So we are aiming to write a project to query those videos by using AI and deep learning approaches. So our AI algorithms actually classify the Pakistani cars from those recorded videos and store into the databases. For example, what type of car crossed which CCTV camera and at what time span, so that if any car is stolen, so the staff member is not bound to watch the whole video. He just can query from the database and retrieve that record. So this is an example. For example, this is input car, and the output is it automatically classified. This is Cultus old model, and this is the color, and so on and so forth. The third project is the offline handwritten text recognition. So this we do with the collaboration of STS, IBA testing services. So offline handwritten text recognition has many algorithms available, but they can only convert such type of text which is shown on the slide. But how about this text? For example, if there is a form which contains name, father name, and so on and so forth. So this can we elicit this information from the handwritten text into the digital text in a structured format. So yes, we can. We have performed some experiments, and we have wrote a prototype to convert this type of form into the structured format. So this algorithm from this form will give us a complete database row. Okay, the name of person is this, father name is this, education is this, gender is this, and this is the picture of this person. The last project is multiple object tracking for aerial view images. So we know multiple object tracking is performed on CCTV footages, but very few authors or researchers have performed multiple object tracking on aerial view images. So we have got a project from 360 Cloud Vision, who has given us the task to, to monitor the traffic and classify the traffic. For example, if on the road there's a car or a heavy vehicle, what's the speed, what's the direction, in which lane it's going, what's the direction, how it is moving from north to south, and so on and so forth. So we generate so many heat maps. We try to convert aerial images into useful database information. So these are some of the outputs of those, algorithms. So currently we have several resources available for AI. For example, we have around 30 GPU-based workstations to train the machine learning models. The machines contain NVIDIA 2080 graphic card. We have RAM up to 32 GB in each machine. We also build our own servers, which contain the CPUs, GPUs, RAM, SSDs. We deploy AI environments such as deep learning environment, CUDA, DNN, TensorFlow, Theano, Trace, and several other platforms to run the AI applications. For deployment, we use the Amazon or Google Cloud services. The challenges we face is in offline, of course, we need to proper schedule the tasks. For example, the 3D60 Cloud Vision, the client requirement is we should run it in online mode as well as the offline mode. So in online mode, we need to take care of speed, scalability, flexibility, and affordability. However, in offline mode, we need to take care of the proper scheduling of the tasks. We are currently looking for some solution of HPC which provide us the affordability, security, speed, scalability, reliability, and backup features where we can deploy our AI models for future serving. So this is our requirement. We are looking for such solutions. So I think the project which Asif Khan and the team from Korea is doing is about HPC for Asia will surely help us in deploying our application on that cloud service. So thank you so much. So this is a brief status of AI at Pakistan, specifically at Sukkur IBA Sukkur. So if you have any question, you're welcome.
Thank you, GM. You've got some very interesting projects on the go over there. Did anyone have any questions for GM? Okay, well, let's move on to our next presenter, Mohammed Salak from Bezmayalan Vakif University in Turkey. Over to you, Mohammed.
Hello everyone. Which screen do you see at the moment?
We can see your presentation. That's coming up.
Okay. All right, great. So hello everyone. Good morning or good afternoon. So I'm going to be talking about multiple sequence alignment of large number of sequences on HPC, and we did a case study of SARS-CoV-2. So with this presentation, I'm just going to talk about the alignments and common problems, and then how we oversolved this problem with a tool that we developed, and we named it as ref alignment. So MSA is multiple sequence alignment is widely used technique in computational biology for biological sequences, and precisely it refers to 3 or more biological sequences, usually DNA, RNA, or protein. And this is one of the first things that we learned when we start into the field of bioinformatics. And it is used to identify the evolutionary relationships and common patterns between genes. And one of the objectives of this MSA is to detect structural or functional similarities between proteins, or comparison of another protein sequences. So these studies, they are traditionally done using alignment dependent approaches. And right now there is also alignment independent approaches that are in the rise, because as the data increases or the diversity increases, it becomes a challenge to actually align these sequences. And there will be a point, for example, if you want to study all the viruses, you cannot possibly align them because there are too many families, too many species. So it will be impossible to align them. And there is a need for these kind of approaches. And of course, alignment independent approaches do not give you the insight of a alignment dependent approaches. So we kind of need both, and I think that's the best will be to combine the two together. But yeah, usually what we do is like alignment dependent approaches. So in here, I just want to show like how the data is growing, and I think this is gonna sound a little bit weird, but thanks to Corona, last year it just hit 1 million sequences, and a year later we have slightly over 12 million sequences. And as I mentioned earlier, aligning it can be pretty challenging. And what we are seeing in here, we are not even talking about different species or families. We are still talking about the same species. And I know that this is special case during this pandemic era, but I think this trend is going to stay there because DBs for all sorts of data types are growing dramatically. Like single cell metagenomics or geo databases, they are all growing like significantly. So we've been trying to align these sequences and we've been having a problem. And luckily there was this tool published recently by Vladimir. And we invited him to give a talk to our lab, and we had a nice convo with him. We discussed how we can overcome the problem of aligning more than 1 million sequences. And it was not very good. I'm going to show it in the next slide. This took like more than 7 days, and trying to fix the alignment, we've been working on it more than 6 months. And this is how the alignment looks like. Because you have too many alignments, it just gets stretched more and more. And what you see in here, it's just slightly over than 1 million sequences. And the average length in the data set is 1273 amino acids. But when you align them, it gets over 15,000 amino acids because of the gaps. And this took like 7 days with a HPC that we used, and it was 1.5 terabyte RAM and 100 CPUs. You try to align them, then you get your results, then you try to fix it, analyze the results again, try to find the culprit sequences, and then try again aligning and stuff. So it took like more than 6 months, but it was not good. So later on, we looked at another tool which has been there for many years. It is developed by Robert Edgar, and actually got into touch with him too. And that convo led to idea of aligning using a reference. And here's a tool that can facilitate that. And we took advantage of that USearch. And so the basic idea behind this one is, instead of aligning all of the sequences, we align them with respect to the reference. Something similar to variant calling and what you do with the NGS analysis, which is actually well studied. So you take a reference sequence and you choose a reference, and then you align it to a reference. So I took USearch, I beefed it up, and kind of improved it, and we added kind of additional parameters to make it work. And then we have our tool. So this is the results after developing our tool RefAligner. So 1 million sequences, the same one, you just align it less than an hour. And since you align them to a reference, it's just, nicely aligned. You don't need to worry about the gaps or stuff. You don't need to even like check your how the alignment is. Yeah, that was it. And I want to thank everyone for their attention. The lab funding from TÜBİTAK and collaboration with Robert Edgar. Yeah, that's all. If there's any questions, I can answer. If not, I'll share my email if anybody wants to keep in touch or find more about it.
Thank you for a really good presentation. and great work in reducing the amount of CPU time that's needed to run your alignments. That's remarkable, the speed up that you've got. Do we have any questions? Okay, let's move on to our next presenter, Ezra Bulsara, who will be talking to us about applying high-performance computing in drug discovery and molecular simulation. Over to you, Ezra.
Okay, you can see my screen, right?
We can see you. That's fine.
Okay. Okay. Hello, everyone. And I'm Ezra Bulsara, and I'm joining from Turkey. And today I will be talking about applying high-performance computing, drug discovery, and molecular simulation. Okay. So as you all are aware, HPC helps us speed up the process that we can collect, manage, store, process, and analyze our data. And it also provides new solutions to world's problems and life science problems through chemistry, genomics, pharmacology. We can use HPC for our modeling, drug discovery, or we can use it for agricultural engineering and many other areas. And traditionally, drug discovery takes more than 10 years, and it requires more than $1 billion for just one drug. And computational drug discovery methodologies like molecular docking and molecular dynamics and many others, it reduced the money and time spent for drug discovery. And these techniques can be accelerated by grid computing, cloud computing, and graphics processing units. And for molecular docking, I want to give you this example. If you want to dock something to a protein, there are databases including more than millions of compounds. These are called ligands or inhibitors. And if you want to dock them, it usually takes months or years. And with molecular docking, you are trying to reduce this number of compounds that are suitable to your protein. And this way, by reducing the number, you are reducing the number of biological assays that are going to take place, which are longer than normal CDD techniques. And one molecular docking usually takes a few seconds to minutes on modern CPUs. But in order to dock millions of compounds, you would need months or years. That's why we require supercomputers that would speed up this process. And MD simulations, molecular dynamic simulations are also used, and these calculate the time-dependent behavior of atoms in molecular systems. And molecular systems of the biological systems include millions of atoms. That's why calculations can take a long time. That's why we require high-performance computing for molecular dynamic simulations. I want to give a case scenario. NORA is a protein that is found in Staphylococcus aureus, which is a bacteria, and NORA protein, it contributes to antibiotic resistance in this bacteria, and it has a variety of inhibitors. So these molecules they are found to be binding to NORA, but they have very different structures. So it is not clear that how they are capable of binding to this NORA protein. So it suggests that NORA has a promiscuous mechanism and it recognizes different substrates, but we don't know how it does that. And this structure is NORA, the protein structure of NORA. So in here, we aim to characterize ligand specificity and promiscuous mechanism of this NORA. And for this, we have obtained the homology model of NORA, and then we process this model with molecular dynamics simulation on GROMACS to examine the stability of this homology model. And after that, from this molecular dynamics simulations, we obtained different conformations of the protein. And we had around 200 inhibitors that are known to bind to NORA. And at the end of the project, we had 8,000 docking runs. And on a conventional computer, it was going to take about a year. And on a workstation, it took about 3 months to complete these 8,000 docking runs. And at the result of our project, we have found the binding sites of this protein, the amino acids that were binding to inhibitors. And also we have found the characteristics of different, how to say, inhibitors. So we have found some groups of inhibitors that were more likely to bind different sides of the NOR-A, and we have characterized these sides of the protein. So this was one of the ways that we can use HPC for health project. And as a conclusion, we need to improve health and sustainable production of food and energy and other areas of life sciences. And HPC will be the game-changing technology that is need to solve our world's problems. And thank you for listening. These are my references. If there are any questions, I can answer, or I will stop.
Thank you for a very great presentation, Ezra. Does anyone have any questions? Okay, let's move on. Sorry, go for it if someone has a question. Okay, let's move on to our next presenter, Wucheng Kwon from KISTI, who will be speaking to us today about deploying Big Data Express for Korea National Institute. Over to you, Wucheng.
Okay, thank you. I'm Wucheng Kwon, and I work in Corona Center in KISTI from Korea. First, I think I'm going to the project. Today, I will present about the project being carried on by KISTI. The goal of the project is to establish a shared research environment for national research institutes through the construction of big data superhighway. Between the 2 years, we call it Kernel R&D together. Today, we will talk about the network infrastructure and ACL management that we built while working on this project. Large-scale data infrastructure is required for scientific data transmission and analysis. However, building a network infrastructure is costly. Instead of building a new network, we should use existing network to solve the problem. So, yesterday proposed a science DMG model. The need for science DMG is to eliminate bottleneck in end-to-end data transfer at a low cost. This can maximize transmission performance by utilizing existing networks at low cost. Left figure is a network configuration diagram of the typical national institute. What is the unique is that it goes through many security equipment in the path from external WAN to the internal DMZ zone and has a complex structure. Right figure is the sensitive network model. It does go through separate security equipment in the path from the WAN area to the DMZ zone and has a simple structure. Science DMG has some characteristics of legacy network. First, separation of business and research traffic, and DTN server focusing on data transfer, and whitelist network access control policy, and end-to-end performance monitoring. When you talk about the science DMG-based network that we built, there are several adjustments to improve TTN network performance. First, the host tuning for TTN node. To improve network performance, you need to tune storage, CPU, and NIC. And second, next to network tuning for TTN node, also you need to tune the TCP protocol and MPU. And we try to build a network that with this factor as much as possible. We have established a network of 8 national research institutes. It is composed of national research institutes in fields such as Oriental medicine, chemical technology, energy research, fusion energy, bioscience, aerospace, and education. This picture is when we input the TTN node. We think the collaboration with network engineer and each national institute was one of most important factors to build a successful network. All national research institutes have different network configuration. The bandwidth of the backbone was all different from 1 to 100 gigabits, but by applying the SenseDMG model, the network was successfully configured. Each detained zone located near the bi-order router and consists of DTN node and Poppe node. The DTN node transfer data. The Poppe node measure the network performance. This figure shows the definition of an access control policy in built-in EMC environment. ACL are measured in the managed in the firewall of DTN switch directly linked to the boot router. This configuration allows only authenticated DTN server to communicate with each other. So we use the Red Hat Ansible to implement the access control policy. Ansible was used by each institute to deploy a ACL policy in batch to DTN switch that exist remotely. This part is the script used to implement the access control policy. As shown in this figure, Ansible has the advantage of being able to manage multiple DTN switches remotely with simple script. We are able to apply to the access control policy collectively through the node list in the upper right. The implement of access control policy results in advantage from 3 perspectives: and first is performance, scalability, and programmable. Performance is automation improve of access control policy deployment performance, and scalability enable ACL code duplication prevention and synchronization. Programmable is enable automation of network operation and access control policy operation. Performance measurement was performed based on disk-to-disk for the transmission performance between 3 research institutes and KISTI. As a data transport tool, and Globus Online was used. In the 10 gigabits environment, performance came out up to 500 megabytes per second, the highest write speed of SSD. Okay, in this presentation, it was time to introduce the actually data science DMG network. Focus on automate centralized access control policy and has advances from the three perspective: performance and scalability and programmability. Thank you very much for listening.
Thank you very much for a very fascinating presentation, and the use of automation tools is really great to see. Did anyone have any questions for Wu-Chang? Okay, well, let's move on to our next speaker, Kihyeon Kim from KISTI, who'll be presenting on Science IoT over the Science DMZ. Over to you, Kihyeon.
Yeah, hi. Can you listen?
Yep, we can hear you fine. Please go ahead. Thank you. We can see your slides.
된 건가? Okay. Hello everyone. I'm Kihyeon Kim, working at KISTI. I'm very glad to present my work here today. The topic for my presentation is Science IoT project of KISTI. At the last Aprp working group session in March this year, I introduced the Science IoT project of KISTI. The Science IoT collects scientific data using IoT network, and it has some use cases such as environmental radiation monitoring and underground environment and safety monitoring. And I explained our relationship with the Science DMG based research platform. And now I will introduce the research we are preparing for the next step. Our research network customers have many institutions that use large research equipment. So we are also receiving requirements from them for data transmission over the radio. These websites are the main requirements from them. First of all, use unlicensed frequency band due to the cost issue, and they also want us to provide fixed position and point-to-point communication between research equipment and over gigabps throughput and minimize frequency interference. In order to achieve the above goals, we are interested in millimeter wave and sub-gigahertz technologies because they can satisfy the unlicensed bands and high throughput requirements. This table indicates that higher frequency band generates more concentrated beam width from the same size antenna. 포인터가 보이나? The narrow beam width is a difficult point for the mobile communication service to track the positions of each mobile nodes and perform targeted beamforming. But on the contrary, in communication between fixed positions, for example, communication between our research equipment. And then the narrow beam width minimize interference with and from other rings. And the left table shows that the effect of signal attenuation by oxygen is particularly high in the two frequency bands, the 60 gigahertz and 119 gigahertz. This high oxygen-induced signal attenuation can generally be an obstacle in long-distance communication, but is an advantage in terms of security and frequency reusability. In the graph on the right, I'm generating when I'm generating a signal at the distance zero position, I'm generating a signal so that my friend is at 1 kilometer distance, and the friend can receive the signal at 30 decibels. Then, in this situation, if there is oxygen absorption, the signal drops to 0 decibel if it goes up to 2.5 kilometers. But if there is no oxygen absorption, the signal drops to 0 decibel if it goes to 32 kilometers. What this means is that I can use the frequency bands with high signal attenuation by oxygen to communicate only with targeted distance and to prevent it from affecting other radio links beyond the distance or eavesdropping on my communication. For these reasons, we would like to conduct a technical study on the 60 gigahertz frequency, because 119 gigahertz doesn't seem to have progressed to the level you can utilize yet. We intend to use 60 gigahertz communication technology for two main purposes. One is increase performance by using multiple communication links with high frequency reuse. Assuming that a large number of 60 gigahertz radio links are placed within an area of 1 kilometer in 3.5 centimeter distance. And then based on recent experiments, we anticipate 1.2 terabps per 1 square meter. And the theoretical limit is 3.7 terabps per 1 square meter. So we can use these multiple short-range radio links to replacement of cable link for scientific research equipment. We expected that. And the right side is long-range radio links. We expect that the long-range radio links is about 1 kilometer communication distance and 1 to 5 gigabps throughput per link. In this case, of course, the multiple links can be placed in parallel, like short-range case. However, no matter how narrow the beam width is, it is also radial. So if it goes very long distance, we have to widen the gap between the parallel links more than in the case of short range. So we are considering only use up to 4 wireless links in this case. And these long-range radio links may used in wireless network backbone for interbuildings and mountain areas. currently, the research is still in the planning stage. About multiple short-range radio links, the similar research is being conducted at APAN in Europe, and there are some Korean researchers participating in the consortium, so we are in contact with them and discussing our research with them. And about the long-range radio link case, we bought commercial 60 gigahertz radio equipment, and we are building a test network. Based on these test results, we will determine the quantitative goals of our future research. This is all. Thank you.
Thank you very much. That's absolutely fascinating work. When do you expect, or do you expect to commercialize some of this research, or are you still in the research phase?
Pardon?
Do you intend to commercialize some of these research into products, or
No,
are you
no.
working on researching?
Just for research, and we will apply this to our national research network users.
That's really great work, and I think we'll all be watching eagerly to see your future progress.
Yeah, thank
this
you.
is Uzin. This is Uzin from the KISTI. Let me give a very short comment about that. The 60 gigahertz radio will be applied for the Kihyeon, one or two links, where the some buildings network has sometimes broken. The wireless will be backup for that kinds of the backup links for the Kihyeon. That is the first applications for the 60 gigahertz.
Excellent.
그거를 스피커도 켜야 돼. 그래야지 선생님.
Do we have any other questions for our presenter? In that case, thank you very much. And let's move on to Alex Mora from King Abdullah University of Science and Technology in Saudi Arabia. Alex will be providing a KISTI country update. So over to you, Alex.
Hi, Howard. Thank you. I hope you hear me well and see my slides.
We can hear you and see you loud and clear.
Okay, thank you. So today I'm going to give a brief update on the KISTI Research Network. KISTI is a university located in Saudi Arabia, and we are a large campus with a small city with many students and faculty living in this small city we have here. And we have a number of different programs for researching in the bioscience, mathematical engineering, electrical computer science, and physical and engineering sciences as well. And in this small city I mentioned, we have a rather large traffic, and these infrastructures is comprised of some international points of presence. We have almost 8,500 network components. We have homes here in the city with about 3,500 homes connected with gigabit fiber. We have a fully meshed core network with 100 gigabits per second, and we also have 100 gigabits per second international connection directly using two different cable systems from the kingdom here, reaching here the campus to Amsterdam and also to Singapore. In this infrastructure, we also have more or less 4,000 Wi-Fi access wireless points and more than 100,000 network ports. In our campus, we also have our HPC center with the Shaheen 2 supercomputer, which is ranked in the top 500. And this is a system that were enabled in 2015. And now we are working on the next stage of this project with the Shaheen 3, which will be announced hopefully in 2023. And Shaheen 3 would be bigger, faster, and consume less power than Shaheen 2. In this HPC area, we have a large number of different areas covering many different scientific projects. Some of them are in the computer visualization area, for example, to try to make computers recognize plankton species in a sample of Red Sea water, or designing wings for Formula One racing car, or computer simulations of earthquakes and quakes on Mars. And also we do support government bodies and companies to predict changes in the climate so they can improve renewable energy production. In the area of international networking, we had this launch of our 100 gig connection internationally, which is physically 4 times 100 cables. 2 cable systems go from here in the nearest largest city called Jeddah to Amsterdam, and also from Jeddah the other 2 cable are going to Singapore Open Exchange in Singapore. And the system is also making now part of the AER, and in which KAUST joined in last APAN 53. And in this cable systems, we run every international connection for KAUST. We also serve some other organizations in the kingdom, and this international connectivity also is for commodity as well for research and education. And this year we joined the effort of the NetSage project run by the Global NOC in Indiana University. Now it's possible to access it and check the utilization of these links I showed. And this is updated in almost real time, and is also a work in progress, because we are in touch with the team there to also start exporting network flow information. Our infrastructure also we have the Science DMZ with 100G enabled components like the DTN and Perf. And we are integrating this monitoring with NetSage. We are refreshing our performance measurements using Perf nodes. And this year we are going to participate in the Supercomputing 22 networking research exhibit in partnership with Caltech. And we are going also to establish direct circuits, VLANs, with the US. Hopefully we're going to reach Pacific Wave and Starlight in Chicago. And in this partnership, to enable support for the supercomputing. We are going to deploy AutoGo, Sense, and Rare free router components in our Science DMZ. We are evaluating joining also the FAB program of the Fabric Testbed project. And we are also evaluating enabling a new programmable network testbed in our campus network that would be also obviously connected to the research and education community. And so to highlight some details about the participation in supercomputing this year, we are going to be giving the support to for the demonstrations to have a path from the US, crossing the Atlantic, arriving in Europe, and from Amsterdam all the way to Singapore. And from there, we are working with partners to extend the circuits to go back to the US. So we are going to support these closing the ring around the globe for the demonstrations this year. And this is another view of the topology that we are working on. And here on the left side, you can see the circuits that were deployed this week to connect Amsterdam to Singapore. And on those circuits, the traffic of the demonstrations of the supercomputing demo will be running. And from Singapore, we are now in touch with the other partners to extend circuits to reach the US through the Pacific side. So that's my update for today. Thank you.
Thank you, Alex. Some really big improvements on the high-speed networking space in your part of the world. And really good to see you participating in the Supercomputing 22 trials. So this brings us to kind of the end. Oh, does anyone have any questions for Alex before we move on? Okay. Well, this kind of brings us towards the end of our APRP session. I'd like to thank all of the speakers for really great presentations. And now I'll hand over to Jeonghoon to provide some closing remarks for our session. Thank you, everyone, and I'll see you at the next APAN meeting. Over to you, Jeonghoon.
Thank you. So thanks to the
Jeonghoon, we're not getting any audio from you.
Okay. Yes, this is Jeonghoon, and thank you for it all over this and the presenters, and for special thanks for the Andrew and the reading session too, and so on. I hope that the next time and we meet, it is face to face in Nepal, 55th. The here, the Connect project and the APRP work activities, we will expand the of the research platform share and take chance to upgrade in. We still have last one mile problem, and we have the indication, and we have the target place how to make the pass guarantee the through fire or something like. Also, is we trying to find out proper the applicants such like agriculture, the weather, or the disaster areas. If possible, as I wanted to adding the HPC areas. So anyway, and the thanks for your attendees and into our APRP working group. Thank you. See you again, APAN. Thank you.
Everyone.
Bye.
Bye.
So thank you, everyone. That brings our APRP session to a close. It's great to work with everyone around the world, and thank you for great presentations today. We'll see you a little bit later.